Okay, exercise 2. Is this a linear programming problem? Provide the basis of your conclusion. Find the maximum value of z where z equals 0.5x plus y, subject to x greater than or equal to 0, y greater than or equal to 2, and y less than or equal to 5 minus x. Okay, we have a find the maximum value of z. It's optimization. Here's the formulation of z. It says z equals 0.5x plus y. That's a linear function. Okay. Now, let's look at the domain. And in this case, this function here is a real valued function of two variables. So the domain are the allowable x, y's. Says they're subject to x greater than or equal to 0. It's linear. Y greater than or equal to 2. That's linear. Y less than or equal to 5 minus x. Also linear. And all the constraints are of the permissible type. One of the three permissible types there. So we see we have a greater than or equal to, greater than or equal to, less than or equal to. Yeah, it's all fits the definition of a linear programming problem. We're ready to conclude. So our answer, yes, exercise 2 is a linear programming problem. It seeks the maximum value of a function, so it is an optimization question. The objective function is linear. We saw that formula. It's linear. The domain of the function is defined by a system of linear constraints. Each constraint is one of the permissible types, less than or equal to, or greater than or equal to. Exercise 4. Is this a linear programming problem? Provide the basis of your conclusion. Find the maximum value of z, where z equals to 0.2x plus 0.4y, subject to quantity x minus 3 squared plus 4 times the quantity y minus 2 squared, less than or equal to 4. Alright, this question does say find the maximum value of z. It's optimization. Z is equal to 0.2x plus 0.4y. It's got a linear formulation. It's a linear function. Okay, how about the domain, the allowable x, y's in this case? Wow, look at that. X minus 3 squared plus 4 times y minus 2 squared. Okay, that is a non-linear inequality there. That will disqualify this question from being a linear programming problem. So what do we say? No, exercise 4 is not a linear programming problem. The domain of the function has a non-linear constraint in its definition. Okay. Exercise 6. Is this a linear programming problem? Provide the basis of your conclusion. Find the maximum value of z, okay, it's optimization, where z equals 0.6x plus 0.2y. Okay, that is a linear function. So far, so good. Subject to xy is a point in region R. Oh, graphic information. Okay, look at that region R. Oh, notice that R is not convex. See, you can take 2 points in R, connect them, and that line segment does not lie entirely in R. So R is not a convex region. Okay, that will disqualify question 6 from being a linear programming problem. Here's our answer. No, exercise 6 is not a linear programming problem. The reason: the graph of the domain is not convex. Thus, the domain is not defined by a system of linear inequalities. We've studied graphing systems of linear inequalities, and one thing we learned that when you graph such a system, you always end up with a convex region that has linear boundaries. Okay. Exercise 8. Z is a function of x and y, and the maximum value of z is sought. Okay, it's an optimization question. A graph including both f and its domain, the feasible region R, is provided. Determine whether or not the problem is a linear programming problem. Explain your conclusion. Alright, let's go to the function f here, this objective function. It's there in the green there. It's a portion of this very curved surface. Okay, that being the case, f is clearly not a linear function, and that will disqualify number 8 as being a linear programming problem. Let's summarize. So, the answer, no, exercise 8 is not a linear programming problem. The graph of the objective function f is a curved surface, and thus f is not a linear function. Remember, had f been a linear function, it would have to be part of a planar surface. Okay. Exercise 10. Z is a function of x and y, and the maximum value of z is sought. Okay, it's optimization. A graph including both f and its domain, the feasible region, R, is provided. Determine whether or not the problem is a linear programming problem. Explain your conclusion. Okay, looking at function f there, the graph. Alright, it is indeed a planar surface, part of a planar surface. So f's a linear function. Let's look at that domain, R there. Okay, look at that. That region R has got a curved boundary for part of it. Well, it's not the result of a system of linear inequalities. If it has some curved boundary, it must have some non-linear inequality in the definition, and that will disqualify 10 as being a linear programming problem. Let's summarize. So our answer, no, exercise 10 is not a linear programming problem. The domain, or feasible region, has a curved line boundary. Thus, the domain has a non-linear inequality in its algebraic definition. Exercise 12. Z is a function of x and y, and the maximum value of z is sought. Okay, we've got an optimization question. A graph including both f and its domain, the feasible region, R, is provided. Determine whether or not the problem is a linear programming problem. Explain your conclusion. Okay, looking first at the graph of the function, f. Okay, it's part of that planar surface there. F has a planar surface graph. Okay, it's a linear function. Good. Let's look at the domain, R. R is a convex region in the xy plane. That's nice. Oh, but look closely. Look at the two of the boundaries of R are dashed lines. Hey, if those are dashed lines, that means those kind of inequalities are not less than or equal to or greater than or equal to. Those kind of inequalities are strictly less than or strictly greater than. And that's not permissible in a linear programming problem. So, exercise 12, disqualified, not linear programming. So, the answer, no, exercise 12 is not a linear programming problem. Why is this? The domain, feasible region, has two dashed line boundaries. Thus, the domain has two strict inequalities such as less than or greater than in its algebraic definition. Okay. Exercise 14. Suppose w is a function of x, y, and z. Now, graphically, what does this mean? A real valued function of 3 variables. Okay, you'd need 4 dimensions to graph it. It's not going to be graphable, but we can still discuss it abstractly, mathematically. Okay, and w is a linear function of x, y, and z. Okay, so actually, so far, this is a linear programming problem. The minimum value of w is sought. Yeah, it's an optimization question. More good news. The graph of f would require 4 dimensions, so cannot be provided. However, the graph of its domain, feasible region S, is provided. Okay. S is the solid triangular prism illustrated, and S contains its boundary surface. Determine whether or not this problem is a linear programming problem. Explain your answer. Okay, well, so far we've got the idea that it is optimization. The function is linear. And now let's look at this domain. It's convex, right? If you choose any 2 points inside that prism there, connect the 2 points, that line segment will lie within S. It's convex. Okay. Now, it needs to contain its boundaries, otherwise those surfaces there would not be a less than or equal to or greater than or equal to type inequality solution. However, this problem says very clearly. S contains its boundary surface. Okay, so that fixes the issue about what kind of constraints we have. Those constraints must indeed be one of the three permissible types, or amongst the three permissible types. You know what? 14 is a linear programming problem. Answer: yes, exercise 14 is a linear programming problem. It seeks the minimum value of a function, so it is an optimization question. The objective function is specified as being linear. The graph of the domain of the function is a convex polyhedral solid, thus can be defined algebraically by a system of linear constraints. The domain S is specified to contain all of its boundary surface, thus each constraint is one of the permissible types, less than or equal to, or greater than or equal to. Okay, great, all done.